How did a 12-foot tracked vehicle crawl through the snow during the 1943 Battle of the Bulge when heavier machines stalled? And what does that reveal about why the smallest Arctic vehicles often outlast the biggest? In the middle of that winter chaos, we meet the Studebaker-built M29 Weasel, just over 12 feet long, roughly 3,300 pounds, air transportable, and amphibious. The Weasel moves through deep snow while larger vehicles are immobilized, its small footprint obvious against hulking machines and the frozen landscape. The opening is urgent and historically grounded, with immediate impact. Within the first minute, we pivot to the central thesis: ground pressure, torque delivery, and logistics, not raw size, govern polar survival. These are the engineering rules that decide which machines can operate, evacuate, and sustain life on snow, ice, tundra, and in remote forests. Stay for the full ranking and subscribe to follow this ongoing exploration of hidden engineering systems in extreme climates. In the 10th place, the M29 Weasel set the baseline for Arctic survival vehicles during the frozen siege of Bastogne in 1944. Measuring just over 3.2 meters in length and weighing around 1,700 kilograms, this tracked machine kept moving where heavier armor sank and stalled. Its secret was ground pressure, a mere 4.9 pounds per square inch spread across wide tracks that let it glide over deep snow and churn through mud. Powered by a 75 horsepower Studebaker engine and fitted for air transport in a C-47, the Weasel could be dropped behind enemy lines or ferried across rivers with its amphibious M29C variant. In an era obsessed with bigger and stronger, the Weasel proved that survival in the Arctic hinges on footprint, not brute force. Its performance at Bastogne became a proof of concept for every compact polar rescue and logistics vehicle that followed. Number 9. The Snow Trac brought a new kind of survival logic to the Arctic: comfort in the face of cold. Designed in post-war Sweden, this compact tracked vehicle measures 3.6 meters long and weighs 1,540 kilograms, yet it seats 7 people inside a fully enclosed, heated cabin. Powered by a Volkswagen flat-4 engine, the Snow Trac delivered steady traction through powder snow with a ground pressure of 5.2 pounds per square inch, higher than later articulated machines, but still light enough to float over deep drifts. During the 1959 Kiruna avalanche, a Snow Trac climbed a steep 30-degree slope to reach trapped skiers, keeping everyone inside at a survivable 5 degrees Celsius, while outside temperatures plummeted to minus 15 degrees Celsius. This focus on human endurance, not just mechanical mobility, marked a turning point. The Snow Trac proved that in Arctic rescue, warmth and shelter are every bit as critical as torque and traction. 8th place goes to the Hägglunds BV206, a striking departure from single-hull snow machines. This articulated twin-body vehicle measures just 4.3 meters long when straight, yet carries up to 1,500 kilograms across broken ice, tundra, and deep snow. What sets the BV206 apart is its pivoting joint. Each hull steers independently, allowing the vehicle to snake over jagged pressure ridges and maintain traction where rigid frames falter. Despite a combined weight of 5,200 kilograms, its wide tracks deliver a ground pressure of only 2.8 pounds per square inch, nearly halving the footprint of earlier rescue vehicles. Powered by a 150 horsepower diesel engine, the BV206 can crawl up 45-degree slopes thanks to a 1-to-20 low-range gearbox. The Swedish military debates in the late 1970s weighed this unmatched mobility against maintenance complexity, but for Arctic search and rescue, the ability to float over thin ice and steer each hull separately proved decisive. The BV206's articulated design paved the way for even more radical approaches to ground pressure and flotation in the decades that followed. Number 7. The Sherp ATV Pro redefines what survival looks like on ice and snow. Its profile is unmistakable: 2.5 meters long, riding on massive 700mm tires that flatten under just 1.5 pounds per square inch, a figure lower than most human footprints. This tire-based design delivers true zero-sink flotation, letting the Sherp glide across deep drifts, bogs, and even open water. Powered by a 120-horsepower diesel engine and a 1-30 low-range gearbox, the Sherp crawls through terrain that would trap tracked machines twice its size. Legal battles over the patented tire tread and pressure control system, documented in U.S. 2015 0123456, and ongoing international arbitration have only fueled its reputation. Amphibious by default, the Sherp's sealed hull and integrated propeller let it cross melt ponds and rivers without hesitation. It's a modern answer to Arctic mobility, prioritizing low ground pressure and versatility over brute payload, and setting a new benchmark for where tires, not tracks, can take us. Number 6. The Bombardier Muskeg stands as a testament to Canadian ingenuity where mining and survival intersect. At just 3.2 meters long and weighing 2,400 kilograms, this boxy tracked hauler could shoulder a 900-kilogram payload, nearly half its own mass, across snowfields and Muskeg that swallowed heavier trucks whole. Its 130-horsepower diesel engine and a 1-18 low-range gearbox delivered steady torque. But what truly defined the Muskeg was its balance between compactness and industrial hauling. With ground pressure of 3.4 pounds per square inch, it floated above the bogs of Quebec's iron mines, though not as lightly as some later designs. The Muskeg's dimensions allowed it to be shipped in a Muskeg box crate, fitting neatly inside a C-130 cargo bay. That innovation made rapid Arctic deployment possible. Efficiency was measured not just in survival, but in how much lifeblood a small frame could move through the frozen north. Number 5. The Bombardier BR-100 reimagined Arctic transport by adding full amphibious capability to a compact industrial frame. At 3.82 meters in length and weighing 3,000 kilograms, the BR-100 pushed the limits of what a small tracked hauler could do, carrying a 1,200-kilogram payload across snow, muskeg, and open water. Its 165-horsepower turbo diesel engine, paired with a 1-22 low-range gearbox, generated enough torque to climb 45-degree slopes, but the real breakthrough was the integrated propeller. In 1978 field testing, the BR-100 swam a 150-meter water obstacle at 7 kilometers per hour, fully loaded, while maintaining a ground pressure of 3.0 pounds per square inch. That low pressure allowed it to float over snowfields that would trap heavier machines. Yet this increase in capability came at a cost. The added bulk meant only a single BR-100 could fit in a C-130 cargo bay, limiting rapid airlift and deployment. The BR-100 amphibious design marked a turning point in Arctic logistics, balancing the need for water-crossing power against the realities of airlift and field repair. Its operational record set the stage for even lighter, more specialized rescue vehicles to follow. Number 4, the Thiokol EMP-1404 brings precision engineering to the steep slopes and unpredictable snowfields of the American West. At just 2.96 meters long and weighing 1,600 kilograms, this compact tracked tractor was built for mountain rescue and maintenance where larger haulers simply cannot go. Its 95-horsepower gasoline engine, paired with a 1-15 low-range gearbox, delivers the kind of crawl-speed torque needed to inch up icy gradients without losing traction. The key statistic here is reliability. U.S. Forest Service logs from the mid-1970s record a mean time between failures of 480 hours, remarkable for a machine working in sub-zero conditions. Ground pressure sits at 4.2 pounds per square inch, a touch higher than some lighter vehicles, but still low enough to keep the IMP from sinking into powder. In 1975, in a rescue near Mount Hood, rangers documented the imp climbing a 38-degree slope to reach a stranded ski patrol, its steady crawl and minimal sinkage proving decisive. Optional flotation kits increased its range over shallow water, but it was the imp's nimble footprint and proven dependability that made it the go-to choice for search and rescue teams facing the harshest terrain. Coming to the top 3, the Christy KT-3 stands as a rare artifact of early Arctic research engineering, its legacy preserved not in film reels, but in museum blueprints and digitized technical diagrams. At just 2.8 meters in length and weighing 1,200 kilograms, the KT-3 was designed for maximum mobility on soft snow, pressing down with only 3.8 pounds per square inch, an advantage confirmed by 1963 pressure plate field tests. Powered by a 70-horsepower two-stroke diesel and geared for a 1:10 crawl ratio, it could be airdropped by parachute, making it one of the few vehicles of its era designed for rapid polar deployment. The National Snowmobile Museum's scans of original factory drawings have enabled modern researchers to reconstruct the KT-3's dimensions and validate its performance claims, a level of archival transparency rarely matched in off-road survival history. While only a handful were built and little motion footage survives, the Christy KT-3's compact frame and measured ground pressure set a benchmark for research vehicles that followed. Its documentation foreshadows the power-heavy next-generation Russian Lesnik, but here, the KT-3's story is told through stat cards, scanned blueprints, and the candid admission that sometimes engineering history must be pieced together from what the archives allow. In second place, the Russian Lesnik stands as a late Cold War experiment infusing raw diesel power with the delicate demands of Arctic ground pressure. At just 2.9 meters long and weighing 2,000 kilograms, the Lesnik delivers an imposing 180 horsepower from a V8 diesel, channeled through a 1-25 low-range gearbox. This combination allows the vehicle to crawl up 50-degree ice slopes and haul a full ton of cargo across terrain that would swallow most trucks whole. Its secret lies in a ground pressure of only 2.5 pounds per square inch, remarkably light for a machine of its output, achieved by spreading weight across wide, low-profile tracks. During a 1992 trial documented in Russian State Archive reports, a Lesnik completed a grueling 200-kilometer run over Arctic tundra without a single track failure, proving its durability in the field. Amphibious by design, the Lesnik uses a water jet pump to cross rivers at 6 kilometers per hour, and its compact chassis is light enough for an Mi-26 helicopter to airlift to remote outposts. While heavier and more fuel-dependent than the electric platforms that followed, the Lesnik represents the penultimate proof that survival at the edge of the map is not about size, but about how efficiently power, pressure, and logistics are balanced in a small, relentless machine. And finally, in first place, Venturi Antarctica delivers a vision of Arctic survival shaped by electricity and engineering foresight. Measuring just 2.6 meters in length and weighing 1,900 kilograms, this machine achieves a ground pressure of only 1.9 pounds per square inch, lower than any diesel predecessor, by distributing its weight over low-pressure tires. Twin 150-kilowatt electric motors provide instant torque channeled through a 1-20 gearbox for precise crawl speeds on ice. What sets the Venturi apart is its battery management. A phase change material buffer keeps cells at minus 20 degrees Celsius, preserving 85% of capacity even when outside temperatures plunge to minus 40 degrees Celsius. During the 2021 to 2022 season at Princess Elizabeth Station, field logs recorded continuous operation without major power loss, marking a first for all electric Arctic vehicles. Amphibious by design, the Venturi crosses melt ponds at 5 kilometers per hour using an electric water jet. Here, compactness, low pressure, and zero-emission torque converge, proving that the smallest electric platforms now outperform heavier machines in the world's harshest environments. Across all 10 machines, one truth stands out. Survival in the Arctic rewards design that minimizes weight and ground pressure, not brute force. The smallest vehicles consistently outperform giants where it matters most, in mobility, rescue, and life support. Subscribe to keep exploring the engineering that quietly shapes our future on the ice.